On an infinite chessboard, a game is played as follows. At the start, n square pawns are arranged on the board, in an n by n block of adjoining squares, one pawn at each square. A move in the game consists of choosing a pawn, and then making it jump, in a vertical or a horizontal direction, over an occupied square, into an adjacent unoccupied square immediately beyond. Then, the pawn, which has been jumped over, is removed. We can go then to the next step, and move another pawn, in case where the conditions mentioned earlier are satisfied. This process can continue until we are in a situation where only one pawn is left, or in case where no legal moves are left. With the choices of the moves of the pawns that we made, we see that no more legal moves are left, and hence the process ends. The main problem: find those values of n, for which the game can end, with only one pawn remaining. For example, let us show that the game can end with only one pawn remaining, in case where n is equal to 4. Similarly, let us show that the game can end with only one pawn remaining, in case where n is equal to 5. In order to find out for which values of n our game can end with only one pawn remaining, let us introduce the following technique, which allows us to reduce the sizes of rectangles of pawns. First, observe that if we have 3 adjacent pawns at the border's bottom, and there are 3 adjacent pawns right above them, then the 3 adjacent pawns at the bottom can be wiped out as follows. Next, let n be a positive integer, which is greater or equal to 3. Then, let us show how to use the previous technique in order to reduce the size of an n by m plus 3 size rectangle of pawns into a rectangle of size n by m. First, we use our technique on the leftmost 3 columns of our rectangle until we are left with only 2 rows. Then, to get rid of the last 2 rows, we use the pawns in the adjacent column. The technique we showed, in order to wipe out the 3 most left columns from our rectangle of pawns, can be used in a similar way in order to wipe out the 3 most bottom rows from our rectangle. Hence, if we start with a square of pawns of size n, then we can reduce its size to n-3 by wiping out the three most left columns, and then wiping out the three most bottom rows. This suggests that we should distinguish between the following three cases. The case where n is equivalent to 0, 1, and 2, respectively, modulo 3. Or equivalently where n is equal to 3k, to 3k plus 1, and to 3k plus 2, where k is a positive integer. First, let us look at the case where n is equal to 3k plus 1. Observe that 3k plus 1 is equivalent to 4, modulo 3. And hence, if for the case where n is equal to 4, we have a solution, then we also have a solution for the case of 3k plus 1. However, we already showed that for the case where n is equal to 4, we have a solution. Hence, the case where n is equal to 3k plus 1 also has a solution. Let us illustrate this visually. In the illustration we have a square of pawns of size 3k plus 1. We start by removing the three leftmost columns. Then, we remove the three rows at the bottom. At the next step, we again remove the three most left columns. And then again, we remove the three rows at the bottom. We repeat this process until we arrive to a square of pawns of size 4. Then, at this stage, we already showed how we can move the pawns in order to finish with only one pawn remaining. Let us check now the case where n is equal to 3k plus 2. Observe that 3k plus 2 is equivalent to 5, modulo 3. Hence, if for the case where n is equal to 5, we have a solution, then the case where n is equal to 3k plus 2 also has a solution. However, we already showed how to solve the case where n is equal to 5. And hence, the case where n is equal to 3k plus 2 also has a solution. Hence, we are left only with the case where n is a multiple of 3, that is, n is equal to 3k. In this case, as in the previous cases, we can convert our problem to the problem of finding a solution for a square of pawns of size 3. However, by checking all the possible combinations of moves for this case, it is not hard to show that it doesn't have a solution. This may suggest that the case where n is equal to 3k does not have a solution for any positive integer k. To prove this, let us color our chessboard in a periodic order of red, blue, and green squares, as in the illustration. Let us consider a square of pawns of size 3k. We assume, by contradiction, that one can move the pawns in such a way that only one pawn will remain in the end. Let us denote by R, B, and G the number of occupied red, blue, and green squares, respectively, at some stage. Observe that each time when a pawn is moved into a red square, then the number of occupied blue and green squares is reduced by 1. That is, R is increased by 1, while B and G are reduced by 1. The same is similarly true in case when a pawn is moved into a blue or a green square. That is, if we think of R, B, and G as an ordered triple. Then, when a pawn is moving to a red square, the vector 1, minus 1, minus 1 is added. Similarly, when a pawn is moving to a blue or a green square, respectively, then the vectors minus 1, 1, minus 1, and minus 1, minus 1, 1 are added. Since we assume, by contradiction, that we can finish our game with only one pawn remaining, we can also assume, without loss of generality, that the last move of this pawn is to a red square. Hence, at the end, we are left with the vector 1, 0, 0. Observe that we start with the vector whose all components are equal to m, where m is equal to n square, divided by 3. And in this case, m is an integer, since, by assumption, n is divisible by 3. This is because, at the beginning the number of occupied red, blue, and green squares are equal, and we have n square pawns. Lastly, let us denote by A, B, and C the number of times for which a pawn moved into a red, blue, and a green square, respectively. Hence, we have the following equality. Equivalently, we have the following system of equations. Since m is an integer, then the solution to this system of equations implies that b and c are not integers, which is a contradiction. Hence, when n is divisible by 3, or equivalently, when n is equal to 3k, for a positive integer k, then there is no solution to our game.